Hello, in this lecture we will find out the size of line segment AE. In the drawing we have square ABCD. We know that line segment BE equals to 2 units. Line segment DE, this line segment equals to 8 units, and we also know that angle BED, this angle equals to 90 degrees. It is a right angle, and we want to find out the size of line segment AE, the size of this line segment. So I will connect together points A and D and E together by a straight line. So we actually want to find out the size of the straight line AE. Okay, so first of all we will connect together points B and D by a straight line. Actually, triangle EBD is a right triangle, so I write it down that triangle EBD is a right triangle. Triangle EBD is a right triangle. So because of the fact that triangle EBD is a right triangle, we can implement the Pythagoras theorem in the right triangle, triangle EBD. And according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle, triangle EBD, the hypotenuse is the red side BD in the red color. So the square of the hypotenuse, it is actually BD square, and it will be equal to the sum of the squares of the perpendiculars. It will be equal to BE square plus DE square. So according to the Pythagoras theorem, in the right triangle, triangle EBD, BD square equals to BE square plus DE square. So BD square equals to BE square. BE equals to 2 units, so BE square is 2 square, 2 square is 4, plus DE square. DE equals to 8 units, so DE square is 8 square, and 8 square is 64. So in total we got that BD square equals to 4 plus 64. 4 plus 64 is 68. So we found out that BD square equals to 68. Here we take a root out of equation number 1, and we will get that BD equals to the square root of 68. Okay, we found out that BD equals to the square root of 68. Actually, BD is also the diagonal of square ABCD, and it equals to the root of 68 square units. We also know that all the angles inside the square are right angles. Therefore, angle BCD equals to 90 degrees. It is a right angle. And angle BAD also equals to 90 degrees. It is also a right angle. I present to you rule number 1, and we will implement the rule in our drawing. According to rule number 1, the diagonals of a square bisect, or also we can use the word cross. So the diagonals of a square bisect the angles of the square into 45 degrees angles. So I will read rule number 1 again. Rule number 1 states that the diagonals of a square bisects the angles of the square into 45 degrees angles. Okay, this is rule number 1. We will implement rule number 1 in our drawing. DB, the segment line in the red color, is the diagonal of square ABCD. Therefore, according to rule number 1, diagonal DB bisects the angles of the square into angles of 45 degrees. That is to say, angle CDB will be equal to 45 degrees, and also angle ADB will be also equal to 45 degrees. Likewise, angle ABC, this angle will be equal to 45 degrees, and angle ABD, this angle will be also equal to 45 degrees according to rule number 1. Okay, so triangle BDC is a right angle because of the fact that this angle is a right angle. So triangle DBC is a right angle. So in the right triangle, triangle DBC, we will define side DC of the right triangle, triangle DBC as y. That is to say, DC equals to y units in its size. And we know that cosinus 45 degrees in the right triangle, triangle DBC, equals to y or dc over db. I will repeat again. In the right triangle DBC, cosinus 45 degrees equals to dc over db. But according to our definition, dc equals to y, and db, we have already found out that db equals to square root of 68. So we actually found out that cosinus 45 degrees equals to y over square root of 68. Okay, we found out that cosinus 45 degrees equals to y over square root of 68. Here we multiply equation number 2 by square root of 68, and we will get that y equals to square root of 68 times cosinus 45 degrees So we found out that y equals to square root of 68 times cosinus 45 degrees. We know that cosinus 45 degrees is square root of 2 over 2, so I write it down. We will get that y equals to square root of 68 times cosinus 45 degrees is square root of 2 over 2. We also know that 68 equals to 34 times 2, so we substitute 68 inside the root by 34 times 2. So we found out that y equals to square root of 34 times 2 times square root of 2 over 2. We have a rule that says that the square root of a times b equals to the square root of a times square root of b. So according to this rule, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2. Okay, and all is multiplied by square root of 2 over 2, and it is equal to y, and this is actually equation number 2. Square root of 2 times square root of 2 is 2. So we found out that y equals to square root of 34 square root of 2 times square root of 2 is 2 over 2. 2 over 2 is 1, so 2 will get cancelled, and we've actually found out that y equals to the square root of 34 units. Y equals to the square root of 34 units. And we also know that all the sides of a square are equal to each other. So all the sides of square A, B, C, D will be equal to the square root of 34 units. So y equals to DC equals to the square root of 34 units, and BC also will be equal to the square root of 34 units. AB will be also equal to the square root of 34 units, and AD will be also equal to the square root of 34 units. Okay, so we actually know the sizes of all line segments and sides in this drawing, and the only missing variable is the size of line segment AE that we are looking for. Okay, so in the next step I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, if a line segment AB subtends two equal angles, on the same side, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So I will read rule number 2 again. Rule number 2 states that if a line segment AB subtends two equal angles on the same side, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So what is the meaning of rule number 2? The meaning of rule number 2 is that if you have line segment AB So we have line segment AB. This is line segment AB. And this line segment AB, subtends two equal angles. So actually we have the first angle that rests on line segment AB, actually angle ACB subtends on line segment AB, or angle ACB rests on line segment AB, and it equals to theta. And we also have the second angle that also subtends on line segment AB, so angle ADB also subtends on line segment AB, or angle ADB rests on line segment AB, and it is also equal to theta. So those two equal angles are both subtend on the same line segment AB. Okay, so this is the reality, that we have two equal angles that are both subtend on the same line segment AB. So according to rule number 2, if this is the reality, then the quadrilateral ABCD, this quadrilateral ABCD is inscribed by a circle. Quadrilateral ABCD, this quadrilateral is inscribed by a circle. Quadrilateral ABCD is inscribed by a circle. Okay, quadrilateral ABCD, this quadrilateral is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. As you can see, indeed, point A, point B, point C, and point D indeed lie on this blue circle. Okay, this is true according to rule number 2. Again, if we have line segment AB, and on line segment AB we have two equal angles that rest on line segment AB, then according to rule number 2, the quadrilateral ABCD, this quadrilateral is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. Okay, so according to rule number 2, we will implement rule number 2 in our drawing. We can implement rule number 2 in our drawing, and I will explain why. Because of the fact that we have here two equal angles, two right angles that subtend on the same segment line BD. Okay, I write it down. Angle BAD that equals to 90 degrees. This angle rests or subtend on segment line DB. On line segment DB. Line segment DB in the red color. And we also have a second angle, angle BED. Angle BED, this angle that also equals to 90 degrees, that subtend on the same line segment BD of DB. So angle BED also subtends on line segment BD. Okay, I will read again. Angle DAB that equals to 90 degrees subtend on line segment DB. This angle subtend on line segment DB. And angle BED that also equals to 90 degrees also subtends on line segment DB. This angle BED that equals to 90 degrees subtend on the same line segment BD in the red color. So according to rule number 2, the quadrilateral AEBD is inscribed by a circle, and the 4 points AEBD lie on that circle. Okay, so we'll implement rule number 2 in our drawing. So according to rule number 2, because of the fact that we have two equal angles that rest on the same segment line BD, then the quadrilateral AEBD, this quadrilateral, is inscribed by a circle, and the 4 points lie on the 4 points AEBD lie on that circle. So the green quadrilateral is inscribed by a circle according to rule number 2, because of the fact that we have two equal angles that rest on the same line segment BD, then the green quadrilateral AEBD lie on inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. So according to rule number 2, quadrilateral AEBD in the green color inscribed by a circle, quadrilateral AEBD is inscribed by a circle. So actually, according to rule number 2, this quadrilateral AEBD is inscribed by this blue circle, or the green quadrilateral. This quadrilateral AEBD is inscribed by this blue circle, and also the 4 points A, E, B, D lie on this blue circle, and indeed you can see from the drawing that the 4 points indeed lie on this blue circle. Okay, so actually this is the implementation of rule number 2 in our drawing. So according to rule number 2, because of the fact that we have two equal angles that subtend on the same segment line BD, then the quadrilateral in the green color is inscribed by this blue circle, and the 4 points A, E, B, D lie on this blue circle. Okay, I will also draw the two right angles that subtend on the same segment line BD. We have the first angle. The first angle is angle ABD. Actually, angle BAD, this angle is actually a right angle, and this right angle rests on line segment BD. Angle BAD that equals to 90 degrees subtend on line segment DB, or angle BAD rests on line segment BD. And we also have a second angle, angle DEB, this angle that is a right angle that subtends on the same line segment BD. So actually, the second angle is also equal to 90 degrees. Angle BED is a right angle, and angle BD rests on the same line segment BD. So those two right angles rest on the same segment line BD, and therefore, according to rule number 2, the quadrilateral AEBD in the green color is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. So we actually arrived to this drawing by implementing rule number 2 in our drawing. By implementing rule number 2 in our drawing, we arrived to this drawing. So in our drawing, we have quadrilateral AEBD that is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. This is the implementation of rule number 2 in our drawing. So in our drawing we have quadrilateral AEBD that is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay? In the next step, I will present to you rule number 3, and we actually, of course, implement rule number 3 in our drawing. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. I will read rule number 3 again. Rule number 3 states that if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So what is the meaning of rule number 3? The meaning of rule number 3 is that if we have quadrilateral ABCD that it is inscribed by this circle, so we have quadrilateral ABCD that it is inscribed by this blue circle. Rule number 3 apply only to quadrilaterals that are inscribed by a circle and not for the other triangles, not to other quadrilaterals, but only it applies only to quadrilaterals that are inscribed by a circle, like in this drawing. So we have quadrilateral ABCD that it is inscribed by this blue circle. So this is quadrilateral ABCD that it is inscribed by this blue circle, and we also know that the size of side AB of quadrilateral ABCD equals to A units, the size of side BC of quadrilateral ABCD equals to B units, and the size of side CD of quadrilateral ABCD equals to 3 units, and the size of side AD of quadrilateral ABCD equals to D units. Then we also have two diagonals to triangle to quadrilateral ABCD. The first diagonal of triangle of quadrilateral ABCD is AC, and the size of diagonal AC is X units, and the size of diagonal BD of quadrilateral ABCD, the size of diagonal BD, it is actually Y units, or BD equals to Y units in its size. Then, according to rule number 3, if we have a quadrilateral that is inscribed by a circle, like in this drawing, then the product of its diagonals, quadrilateral ABCD has two diagonals. Diagonal BD equals to Y units in its size, and diagonal AC equals to X units in its size. So the product of its diagonals, it is actually X times Y, and X times Y, according to rule number 3, equals to the sum of the products of its opposite sides. The quadrilateral ABCD has two pairs of opposite sides. The first pair of opposite sides, it is actually side BC is opposite to side AD, and the second pair of opposite sides is actually side AB is opposite to side CD. So the product of the first pair of opposite sides is B times D. This is the product of the first pair of opposite sides, and the second product of the second pair of opposite sides, it is actually A times C. And according to rule number 3, the sum of the products of the opposite sides, that is to say BD plus AC, equals to the products of its diagonals, that is to say X times Y, or X times Y, that is the product of its diagonals, equals to the sum of the products of its opposite sides, that is actually BD plus AC. This is the sum of the product, because the first product is BD and the second product is AC, and the sum of the product, it is actually BD plus AC, and it equals to the product of its diagonals, that is to say X times Y. Okay, so that is actually the meaning of rule number 3. If you have a quadrilateral ABCD, that could be any quadrilateral that is inscribed by a circle. If this is the reality, then you can implement rule number 3. It is valid only on quadrilateral that are inscribed by a circle. Otherwise, rule number 3 is not valid. So only if we have quadrilateral ABC that is inscribed by a circle, like in this drawing, then the product of its diagonals, that is to say X times Y, equals to the sum of the products of its opposite sides. And the sum of the products of its opposite sides, it is actually BD plus AC, because B times D is the first product of its opposite sides, A times C is the second product of its opposite sides, and the sum of the products of its opposite sides, it is actually the first product plus the second product, or BD plus AC, that is the sum of the product of its opposite sides, equals to X times Y, that is the product of its diagonals. Okay, that is the meaning of rule number 3. Now we will actually, of course, implement rule number 3 in our specific drawing. We actually know that we arrived to this drawing. We arrived to this drawing by implementing rule number 2 in our drawing. We implemented rule number 2 in our original drawing, and we arrived to this drawing by implementing rule number 2 in this original drawing. So we have this quadrilateral AEBD that is described by this blue circle. Therefore, we can implement rule number 3 in this drawing. Why? Because we have quadrilateral. Whenever we have quadrilateral that is described by a circle, we can implement rule number 3. Okay? The reason that we can implement rule number 3 is because of the fact that we have quadrilateral that is inscribed by this blue circle. Therefore, we can implement rule number 3 in this drawing. And according to rule number 3, if we have a quadrilateral that is inscribed by a circle, then the product of its diagonals, that is to say AB times DE, equals to the sum of the products of its opposite sides. Again, quadrilateral ABCD has two pairs of opposite sides. Side AE is opposite to side DE, and side AD is opposite to side EB. So the first product is the product of the first opposite sides, that is to say AE times DB. AE times DB is the first product of its opposite sides, because AE is opposite to DB, and the product of those two opposite sides is AE times DB. And the second product of its opposite sides, we know also that AD is opposite to EB. So the product of those two opposite sides, it is actually AD plus EB, AD times EB. AD times EB is the second product of quadrilateral AEBD. Okay, the second product of the opposite sides of quadrilateral AEBD is AD times EB. And according to rule number 3, the sum of the product of its opposite sides, that is to say AE times DB plus AD times EB, will be equal to the product of its diagonals. And the product of its diagonals, as you can see from the drawing, quadrilateral AEBD has two diagonals, diagonal AB and diagonal DE, and the product of its diagonals is AB times DE. And that product equals to the sum of the products of its opposite sides. The first product of its opposite sides is AE times DB, and the second product of its opposite sides is AD times AB, and the sum of the product of its opposite sides equals to AE times DB plus AD times EB, and that sum of the product of its opposite sides equals to the product of its diagonals, that is to say equals to AB times DE. Okay, that is actually the implementation of rule number 3 in our drawing. So here equation number 3 is the implementation of rule number 3 in our drawing. Okay, now the only thing that is left to do is to put the data inside equation number 3, and in this way we will find out the missing line segment AE that we are looking for. Okay, so I will copy again equation number 3 in this page, and we will substitute all the variables by the values of those variables. So equation number 3 states that AB times DE, according to rule number 3, AB times DE equals to AE times DB plus AD times EB. Okay, I will repeat again. Equation number 3 is the implementation of rule number 3 in our drawing. Okay. So AB, from the original drawing, we can see that AB equals to the square root of 34. Okay, AB equals to the square root of 34. And what is the size of DE? The size of DE from the original drawing, we can see that DE equals to 8 units. It is given us in the question. So DE equals to 8 units. It is given us in the question. And all equals to AE. AE is the missing variable that we are looking for. So we will leave it as it is. It will be the only missing variable times dB. What is the size of dB? We have already found out that the size of dB, the line in the red color, equals to the square root of 68 units. dB equals to the square root of 68 units. And what is the size of AD? The size of AD is one side of quadrilateral ABC sides, and all the sides are equal to the square root of 34. Therefore, AD equals to the square root of 34. And what is the size of EB? The size of EB equals to 2 units. It is given us in the question. So, as you can see here, we have all the variables of equation number 3, and the only missing variable is AE. Okay, so it will be very simple to find out the size of line segment AE because it is the only missing variable. Okay, here we know that 68 is 34 times 2, so we'll substitute 68 here by 34 times 2, and we will get that the square root of 34 times 8 equals to AE is the missing variable, missing line segment. So instead of 68, we will write down 34 times 2, that equals to 68, plus square root of 34 times 2, according to the rule that the square root of A times B equals to the square root of A times square root of B. The square root of 34 times 2 will be equal to the square root of 34 times square root of 2, and plus square root of 34 times 2, and AE times this expression, all equals to square root of 34 times 8. This is equation number 3. So here we will divide equation number 3 by square root of 34. So square root of 34 will get cancelled. And what is left after we cancelled square root of 34? What is left? It is actually 8 equals to square root of 2 times AE, is the missing line segment, plus 2. So here we will subtract from equation number 3 2, and we will get that 8 minus 2 is 6. 6 equals to the square root of 2 times AE. So here we will divide equation number 3 by square root of 2, and we will get the value of AE that we are looking for. We will find out actually that the size of line segment AE according to equation number 3, equals to 6 over square root of 2. Okay, so we found out that the size of line segment AE equals to the 6 over square root of 2 units. We can simplify this expression because we know that 6 is 3 times 2. So AE equals to 6 is 3 times 2 over square root of 2. Here we will multiply this expression by square root of 2 and then we will divide it by square root of 2, so we change nothing. So it is allowable. And we will get that AE equals to 3 times 2 over square root of 2. We will multiply this expression by square root of 2 and we will divide it by square root of 2. So here in the denominator we have square root of 2 times square root of 2 is 2. So we got that AE equals to 3 times 2 times square root of 2 over 2. 2 over 2 is 1, so 2 will get cancelled. And we actually found out that the size of line segment AE that we are looking for equals to 3 times square root of 2 units, or in terms of numbers, it equals to 4.243 units. Okay, so I will repeat again. We actually found out that the size of this line segment AE equals to either to 3 times square root of 2 units, or in terms of numbers, the size of this line segment AE equals to 4.243 units. Okay, that is the answer to the question. Now I will summarize the lecture. Actually, we wanted to find out the size of line segment AE, this line segment in the red line, and we have square ABCD, and we know that line segment EB equals to 2 units, line segment DE equals to 8 units. And we want to find out the size of line segment AE. And we also know that this angle BED equals to 90 degrees, and we want to find out the size of line segment AE. So we actually connected together points D and B by a straight line. We created this red line DB. Actually, as you can see from the drawing, triangle DEB is a right angle because of the fact that this angle is a right angle. And we can implement the Pythagoras theorem in the right triangle DEB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle DEB is DB, so DB square will be equal to EB square plus DE square. Again, according to the Pythagoras theorem, in the right triangle DEB, DB square equals to EB square plus DE square. But we know that EB equals to 2 units, this is given us in the question, so BE square will be equal to 2 square, 2 square is 4. And we also know it is given us in the question that DE equals to 8 units. So DE squared is 8 squared. 8 squared is 64. So BD squared equals to 4 plus 64. 4 plus 64 is 68. So we found out that DB squared equals to 68. We took out the root of equation number 1 and we get that the size of BE it is actually square root of 68 units. So we can write here that the red line, 970 dB, it is actually also the diagonal of square ABCD. It equals to the square root of 68 units. Then I presented to you rule number 1. According to rule number 1, the diagonals of a square bisect or cross the angles of the square into 45 degrees angles. Okay, so here we have diagonal DB of square ABCD, and according to rule number 1, this diagonal DB bisects or cross the angles of square ABCD into 45 degrees. That is to say, this angle will be equal to 45 degrees, and this angle also equals to 45 degrees. Why? Because it bisects the angle. Okay, it divides it to two equal angles. So this angle is 45 degrees, and this angle is also equals to 45 degrees. Likewise, this angle equals to 45 degrees, and this angle will be also equal to 45 degrees. So we know that all the angles inside square ABCD are right angles. Therefore, this angle BCD, it is a right angle. Therefore, triangle BCD is a right triangle. So in the right triangle BCD, we know that cosinus 45 degrees equals to BC equals to DC over DB. Again, in the right triangle BCD, cosinus 45 degrees equals to DC over DB. And we define DC as Y, that is to say DC equals to Y. So in the right triangle DBC, cosinus 45 degrees equals to DC over dB, and we define DC as Y, that is to say DC equals to Y, so we substitute DC by Y, and we have already found out that dB equals to the square root of 68 units, so we can substitute also dB by the root of 68, square root of 68 units. So we found out that cosinus 45 degrees equals to Y over the square root of 68. Okay, we will multiply equation number 2 by the square root of 68 units, and we arrived at to equation number 2 that says that Y equals to the square root of 68 times cosinus 45 degrees. We know that the value of cosinus 45 degrees is root 2, square root of 2 over 2. Okay, so we substitute cosinus 45 degrees by square root of 2 over 2. So Y equals to the square root of 68 times square root of 2 over 2. And we also know that 68, it is actually 34 times 2. It equals to 68, so we can substitute 68 inside this root by 34 times 2. So we substituted 68 by 34 times 2, and we got that Y equals to the square root of 34 times 2 times square root of 2 over 2. But we have the rule that the square root of A times B equals to the square root of A times square root of B. And so according to this rule, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2. Okay, so Y equals to the square root of 34 times square root of 2 times square root of 2 over 2. And we know that square root of 2 times square root of 2 is 2. So we got here that Y equals to the square root of 34 times 2 over 2. 2 over 2 is 1, so 2 will get cancelled, and we found out actually that y equals to the square root of 34 units. Y equals to the square root of 34 units, and because of the fact that all the sides of a square are equal to each other, all the sides of square ABCD will be equal to the square root of 34 units. DC equals to the square root of 34 units, BC equals to the square root of 34 units, AB equals to the square root of 34 units, and AD also equals to the square root of 34 units. And then I presented to you rule number 2. According to rule number 2, if a line segment AB subtends two equal angles on the same side, then the quadrilateral ABCD is inscribed by a circle, and points A, B, C, and D lie on that circle. So what is the meaning of rule number 2? The meaning of rule number 2 is that if we have line segment AB, we have only line segment AB. Without this circle, we have only line segment AB. And we have two equal angles. Those two angles are both equal to theta. They are equal to each other. And they rest on the same line segment AB. Okay, so if we have two equal angles that rest on the same line segment on the same side, then according to rule number 2, then the quadrilateral ABCD, this quadrilateral is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. So whenever we have two angles that rest on the same line segment from the same side, then the quadrilateral that created from those two angles and the line segment AB, in this case it is quadrilateral ABCD, is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. And as you can see, indeed, those 4 points indeed lie on this blue circle. So this is the meaning of rule number 2. If you have two equal angles that rest on the same line segment, then the quadrilateral that was created from the two angles and the line segment, in this case is quadrilateral ABCD, this quadrilateral will be inscribed by a circle. In this case, quadrilateral ABCD is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. Okay? So this is the meaning of rule number 2, and we implemented rule number 2 in our drawing. We can implement rule number 2 in our drawing. Why? Because we have here two equal angles. Those angle BAD equals to 90 degrees, and angle BED also equals to 90 degrees. So those two angles are equal to each other, and they are both rest on the same line segment BD. And therefore, according to rule number 2, the quadrilateral AEBD in the green color is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. So we can implement rule number 2 in our drawing. Why? Because we have two equal angles that rest on the same line segment. Therefore, the quadrilateral in the green color AEBD will be inscribed by a blue circle, and the 4 points A, E, B, and D will lie on this blue circle. I will repeat again here. We have quadrilateral BAD equals to 90 degrees, and it's subtend on the red line segment BD, and also angle BAD or angle BAD. This angle is a right angle, it rests on line segment DB. So we have two equal angles. They are both rest on the same line segment BD. Therefore, according to rule number 2, I will show it on the drawing. We have angle DAB, that is a right angle, and angle DAB rests on line segment DB, and angle DEB, that is also, or angle BED, that is also a right angle, is also rests on the same line segment BD. So we have here two equal angles. They are both right angles, and they are both lie on the same line segment BD. Therefore, according to rule number 2, this green quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. And indeed, you can see that those 4 points lie on this blue circle. Okay, so this drawing, it is actually the implementation of rule number 2 in our original drawing. This original drawing. So we arrive to this drawing by implementing rule number 2 in this original drawing. So in our drawing we have quadrilateral AEBD in the green color that is inscribed by this blue circle, and we also have 4 points, point A, point E, point B, and point D, that lie on this blue circle. Okay, so by implementing rule number 2, we actually arrive to this drawing. So we actually have quadrilateral, the green quadrilateral that is inscribed by the blue circle. Okay, this is the drawing that we have, and we arrive to this drawing by implementing rule number 2 in our original drawing, in this drawing. And I also presented to you rule number 3, and we implemented rule number 3 in this drawing. Okay, according to rule number 3, if quadrilateral ABCD is inscribed by a circle, and then the product of its diagonals equals to the sum of the products of its opposite sides. So what is the meaning of rule number 3? The meaning of rule number 3 is actually, if we have quadrilateral ABCD, as you can see, the red quadrilateral ABCD is inscribed by this blue circle. Okay, so first of all, in order to implement rule number 3, you must add quadrilateral that is inscribed by a circle, like in this drawing. So if we have quadrilateral that is inscribed by a circle, like in this drawing, quadrilateral ABCD is inscribed by this blue circle, then according to rule number 3, and also quadrilateral ABCD has two diagonals. It has diagonal AC that is equals to X units in size, and it has also diagonal BD that is equals to Y units in its size. Then according to rule number 3, whenever you have quadrilateral that is inscribed by a circle, and in this drawing, then the product of its diagonals, that is to say X times Y, equals to the sum of the products of its opposite sides. And the sum of the products of its opposite sides is as follows. Quadrilateral ABCD has two pairs of opposite sides. Side AD, the first pair is side AD is opposite to side BC, and the second pair of opposite sides, it is actually side AB is opposite to side DC. So the first pair of opposite sides is AD and BC. AD equals to D units in size, and BC equals to B units in size, and the product of those two opposite sides is B times D. and the product of the second opposite sides. Side AB is opposite to side DC, and the product of those two opposite sides, it is actually A times C. So we have two products of the two pairs of opposite sides, and the sum of the products of those two opposite sides, it is actually BD plus AC. Okay, so the sum of the products of the opposite sides is BD times AC, is BD plus AC, and that sum equals to the products of its diagonals, that is to say x times y. Again, the product of its diagonals, that is to say x times y, equals to the sum of the products of its opposite sides, that is actually BD plus AC. Okay? And then we actually implemented rule number 3 in our drawing, and I will repeat again. We arrived to this drawing by implementing rule number 2 in the original drawing. In this original drawing, we arrived to this drawing by implementing rule number 2 in the original drawing. So we have quadrilateral AEBD in the green color that is inscribed by this blue circle. So you can see that you can implement rule number 3 in this drawing. Why? Because you have quadrilateral that is inscribed by a circle, therefore we can implement rule number 3 in this drawing. And according to rule number 3, because of the fact that we have quadrilateral that is inscribed by a circle, then the product of its diagonals, quadrilateral AEBD, has two diagonals, diagonal AB and diagonal DE, and the product of its diagonals is simply AB times DE. AB times DE is the product of quadrilateral AEBD diagonals. Diagonal AB times diagonal DE is the product of those two triangles. So AB times DE, the product of its diagonals, equals to the sum of the products of its opposite sides. Again, quadrilateral AEBD is two pairs of opposite sides. AE is opposite to DB and AD is opposite to EB. So the first product of its opposite sides is actually AE times DB, AE times DB, and the first product of its opposite sides is actually AD times EB, and the sum of the product of its opposite sides is AE times DB plus AD times EB. And according to rule number 3, the product of its diagonals, that is AB times DE, equals to the sum of the product of its opposite sides, that is AE times DB plus AD times EB. Okay, so actually here equation number 3 is the implementation of rule number 3 in our drawing. Okay, then I copy it again, equation number 3, and we put the data inside equation number 3. We know all the variables inside this equation. The only missing variable is the AE, is the missing line segment that we want to find out. We know that AB equals to square root of 34. We know that DE equals to 8 units. We also, AE is the missing variable, missing line segment. We know that DB equals to square root of 68. And we also know that AD equals to square root of 34. AD equals to square root of 34, and EB equals to 2 units. It is given us in the question. So we put the data inside the question number 3, and we got to this equality. And we also know that 68 is 34 times 2. So we can substitute 68 by 34 times 2. And we also know, so we got to this equality. And we also know that the square root of a times b equals to the square root a times square root b. Therefore, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2. Okay? So we got to this equality. Here we can divide the equation number 3 by square root of 34. We divided the equation number 3 by square root of 34. And what is left after? we divided the equation number 3 by square root of 34. What is left? It is actually 8 equals to the square root of 2 times AE plus 2. We subtracted from equation number 3 2. 8 minus 2 is 6, so 6 equals to square root of 2 times AE. Here we divided the equation number 3 by square root of 2 and we got the value of AE. AE actually equals to 6 over square root of 2. We know that 6 equals to 3 times 2, so we substituted 6 by 3 times 2. So we have this equality. Here we multiplied this equation by square root of 2 and then we divided it by square root of 2, so we changed nothing. We got this quality. In the denominator we have square root of 2 times square root of 2. Square root of 2 times square root of 2 is 2. So in total we have 3 times 2 times square root of 2 over 2. 2 over 2 is 1, so 2 will get cancelled. And we left only with the final answer for the value of line segment AE. AE equals to 3 times square root of 2 units, or in terms of numbers, AE equals to 4.243 units. I repeat again, the size of line segment AE that we are looking for equals to either to 3 times square root of 2 units, or in terms of numbers, the size of this line segment AE equals to 4.243 units. Again, equals to 4.243 units. Okay? Thank you very much.